Please welcome Senior Vice President and GM with Cadence, Boyd Phelps.
Look who's right. The lights are bright. It's an honor really to be here today with you at the Intel Foundry Direct Connect. I have a strong connection with many of the teams at Intel, having worked there for 25 years before I came to Cadence, and I essentially was raised in the industry of semiconductor architecture design and technology development while at Intel with some of really the brightest and hardest working people that I've known. So it's really exciting to see the progress on 18A and 18AP and the possibilities it brings for Intel Foundry and certainly for its present and future customers. Now, I would be remiss or incredibly out of fashion if I didn't talk for a second about all things AI. AI from an IP development and an EDA efficiency perspective is at the center really of all of our day-to-day efforts. The pace is furious and the standards, speeds, feeds, and efficiency needs, they continue to only accelerate well beyond, say, even the pace of Moore's Law. And so the demand for innovation and cooperation in the industry and design ecosystems really has never been more important than it is today. So I'll discuss the importance of a curated portfolio and a roadmap tailored for the system foundry, which is essential for the thriving in the AI era and helping customers really get to market faster. I think that's what we're all trying to do, is get our customers to market faster. So, and also the concept of a closed loop refers to our strategy of design technology co-optimization with intellectual property and process improvements, ensuring really efficiency and innovation, that those remain robust. And this closed loop, we want it to invite partnership and shared visions for success in this kind of this transformative landscape. It takes all of us working together. So additionally, and you've heard it talked about a lot, leveraging the packaging advantages that Intel has is crucial for enhancing performance and scalability. Intel Foundry brings not only really a solid process technology to market, but has a key packaging capabilities that complement and even enhance the value of 18A and 18AP. So in terms of AI, there's really three major phases in time and three fundamental layers of AI in its impact to silicon and system design complexity that essentially start out as trying to accelerate compute algorithms and evolve to a greater focus on principled simulation and optimization with the hope of achieving something closer to what people think of as real intelligence. Now, in the industry, we've been immersed in the massive build out of what we call infrastructure AI, consuming tremendous energy and effort with the effort of increasing productivity. It's really lately been all about productivity in the near term with some of the initial monetization attempts centering on agentic AI. Language processing, parsing, intuiting, LLMs are at the heart really of this phase. But what's really fascinating for me to be a part of and witness is the advent of this second horizon of what we call physical AI. AI driven by autonomy and senses, the world of autonomous cars, drones, robots, everywhere, even in your fabs, with domain-specific silicon. That will be transformational. However, it's doubtful that it will approach, say, superintelligence, but make no mistake, this phase 2, will truly transform how we live, whereas the first phase really transforms our productivity. And the third phase of AI will be in the realm of life sciences, from DNA to rapid molecular design to deep understanding of large life science systems that no longer rely on prediction and iterative estimation. All of this creates the background, together with an increasing world GDP, estimates which show that the foundry business can be doubling to nearly 300 to 400 billion by the end of the decade and growing to 700 billion by 2035. So certainly the foundry can be very good business indeed. In terms of industry trends that are driving semiconductor growth, I think one that I really harp on is this notion of disaggregation. And this is really, you saw Kevin with his example there, how important disaggregation is. With the cost of advanced silicon increasing rapidly and the time to silicon maturity slowing, large monolithic designs on advanced nodes are becoming increasingly rare and maybe unsustainable. They take longer to ramp up the yield curve, especially with ever increasing transistor densities, manufacturing times, and MPW costs. Thankfully, packaging technology is probably now as important as Moore's Law. And advances in packaging technology have unlocked the possibility of new architectures, which is key, where companies can move away from expensive and hard to develop monolithic designs on the latest nodes. They can now put the right IP on the right transistor, on the right process node for the right cost. So disaggregation, I think, is here in full force. This is the key to lowering both product and R&D costs and increases the need for IP across this new paradigm of compute. So HPC and AI, they also bring forth new demands for compute performance. They create need, as I said, for new architectures, new memory, and compute paradigms, and especially so with advanced process implementations. Process and architecture are intertwined, certainly. Now, companies they're also overwhelmed with their customers' needs for segmentation. No longer just merchant silicon cut it. Many of the tier 1 and tier 2 companies can no longer afford to develop all of the IP and designs they used to in the past. This is why the ecosystem is so important. They need to focus more on what uniquely differentiates them and buy the rest now more than ever before. And something else that obviously we're witnessing is governments are now ever conscious of the geopolitical environment today and its multitude of risks. They care intensely about silicon self-reliance in this increasingly complex geopolitical environment. Investments are now being made across the globe to build resiliency in the face of uncertain times and unpredictable challenges. As we touched on the topic of disaggregation and chiplets as key contributors to the growing semiconductor TAM, I'd like to share also today, as was presented, that we are a founding member of the Intel Foundry Chiplet Alliance and are pleased to extend Cadence's substantial relationships with the U.S. aerospace and defense sectors and further contribute to advancing the use of our cutting-edge EDA and IP, silicon and packaging technologies, really to enhance our military aerospace defense capabilities along with other commercial sectors. Well, that's exciting. As I mentioned, the foundry business, the opportunity will be as large as $400 billion in 2030. You heard Anirudh say maybe we're underestimating that. $700 billion in 2035. And AI demand alone is driving more than 20% of this CAGR throughout 2030. But all sectors from a silicon perspective are growing, and especially as we move into the phase of physical AI. And it costs more. It costs more to move data than to operate on it. So designing for efficient data movement via memory interfaces as well as high-speed I/O interfaces is vital. Chief scientist at NVIDIA, Bill Daly, he said, locality is efficiency, efficiency is power, power is performance, and performance is king. And disaggregation to address the die size, right transistor on right node problem makes interfaces such as UCIe even more essential, especially as the speeds and feeds and need for efficiency continue to accelerate. So protocol standards and speeds continue to advance rapidly. This is key. We're going to continue to see this. Process technology advancements are essential to provide the best performance possible for these latest and greatest elements of the SoC constructor's toolbox. So now data centers they've progressed from, say, traditional HPC compute virtualization to accommodating AI customers who conduct training and inference on GPUs and XPUs at scale. At factory scale, there are significantly large AI dedicated nodes utilized by fewer tenants really for extended AI training tasks compared to conventional data centers. The compute and communication paradigms have evolved. Corresponding protocols supporting these operations have also advanced. So a computing node in an AI factory typically connects a CPU to an accelerator and NICs using standard protocols such as PCIe and CXL. These accelerators require optimized communication protocols to efficiently manage the memory-intensive traffic generated and that are consumed during AI algorithm execution. HBM remains the preferred memory attachment interface for high-performance accelerators. The data generation and consumption patterns of these accelerators differ substantially from other HPC applications or general-purpose cloud computing scenarios. So to address bottlenecks or overhead associated with existing standards, the industry has introduced the Ultra Accelerator Link and Ultra Ethernet to enhance the capabilities of these AI data centers and factories, ushering in really what we call the era of ultra-efficient computing. So at Cadence, we've been hard at work, working with Intel and been a proud partner with Intel Foundry, even preceding 18A. And with 18A and 18AP, we've collaborated on building a portfolio that meets the most demanding needs really for the HPC and AI and ML world. Cadence, we're announcing an extension to our portfolio of IP at Intel's Foundry, available today. 224 gig SerDes with long-range performance for UA-Link and Ultra Ethernet, the latest standards for scaling up and out in AI factories. A versatile set of options, for memory applications, even DDR5 12.8. MRDIMM Gen 2 support with DDR5, also 8400 with multi-standard support. UCIe 1.1, at 48 gig for advanced packaging that seamlessly facilitates multi-die system and package integration for scalable chiplet architectures. And advanced computing and peripheral connectivity IP is also very important, with the latest consumer standards enabling scalable embedded applications for a wide range of consumer and mobile requirements. So kind of the workhorse IP, a 10 gig multi-protocol SerDes supporting PCIe, Express 3.0, DisplayPort, Ethernet, USB 3.1, 3.2, embedded USB 2v2, which is very important right now in advanced nodes, and MIPI SoundWire I3S. So all these additions complement the already available 112 gig SerDes with extended long-range performance, already complement our 64 gig MP5 for PCI Express 6.0, CXL 3.0, 56 gig Ethernet, and then also LP5 5X 8533 with multi-standard support, and UCIe 1.0 would already exist for 16 gigahertz for advanced packaging. So providing customers really with this broad range of IP options for AI, ML, and HPC and mobile applications, leveraging Intel's RibbonFET and PowerVia technology, and we'll talk a little bit more about that in a second. So further, Cadence, we have a portfolio of other sought-after titles that we look really forward to bringing to Intel 18AP and its successor nodes also as we go forward. So, but first I want to take a second and just say a moment and congratulate the Intel team on really its first major customer delivery on 18A. Congratulations to Kevin, to Ben, to Mike, Yaron, Ron, and really so many others. It's really, I think, should be a proud moment. Lip-Bu, you have a great team. What makes 18A, in my mind, even more remarkable is that it incorporates two distinct process revolutions. Not evolutions, but revolutions. And usually just one is enough of a challenge in any generation, let alone two. 18A is the first process to combine RibbonFET and PowerVia in one node, fully EDA and IP enabled. So, Intel Foundry, you really should feel proud. Congratulations. So the benefit of 18A and 18AP was certainly made more valuable with the close collaboration between design and technology development teams. This is really key for any technology going forward. It's fundamental. I'd like to highlight really some of the benefits that we've seen at Cadence as a result of developing IP. So the definition of a 5-layer backside metal stack was optimal with TD incorporating efficiency in routing, integration, power delivery, yield, and cost. This enabled us to achieve kind of several advantages leveraging the backside metal layers. So the usage for key signal routing on the backside led to a reduction in needed front side metal layer count by 2 layers, and area reduction we could achieve of 15% on some key circuits. So this ability to, and also one that's key, the ability to route key clock nets with less skew and greater reach, improving timing and convergence using the backside metals 1 and 2 for local and backside metals 3 and 4 for global clocking. Also, all of our level shifter standard cell layout and cutouts become even more efficient with backside metal. So the efficient ways in which backside metal can be used to solve critical design challenges in IP, that will continue to proliferate over time and from generation to generation. Now, in advanced nodes, power density is increasing as area shrinks. Metal lines getting thinner and more resistive. This leads to the difficult issue of higher IR drop. So we took advantage of the thick backside metal layers to optimize the power grid strip widths and achieve electromigration targets with near 0 layout iterations, which was pretty phenomenal. And thick backside metal significantly reduces the IR drop so that voltage guard bands for IR drops could be reduced by as much as 20%. And why that is important is because you can now then release that voltage back to the team to be able to use for design frequency uplift or power benefit if you'd like. The other advantage of backside metal extends to areas of designs where perhaps they're a little more esoteric and not so rapidly obvious, but really just as important. And one example is with the LCVCO for our multi-gigahertz clocking of our PCI Gen 6 design. So we were able to design a much higher quality inductor with tighter operation and hence lower power, as design didn't have to overcompensate for unnecessary spread, and we could return that goodness to the IP directly in PPA. So many unique ways in which it can be used. But one thing I want to highlight is perhaps what is not discussed enough with the addition of backside metal and ribbon FET technology is that Intel Foundry really has a best-in-class MEM capacitance density. This becomes a vital tool in the designer's toolbox to reduce things like peak-to-peak I/O noise and digital circuits, and even optimize area by as much as 10% in some key circuits. And in some designs, one can even reduce the need for expensive deep trench capacitors and interposer designs. So while Intel's high-density MEM cap may not be, say, a revolutionary technology advancement, say as like backside metal or ribbon FET modules themselves, it certainly does create a distinct opportunity to improve power, performance, area, and cost for many. Okay, so as important as the DTCO at the process level activities are the co-optimization at what I call the tools, the flows, and the methodology, TFM. This DTCO at the TFM level is just as important. So Cadence's EDA DTCO on 18A at the library level improved ISO power and performance by 2%. Now Cadence TFM was enhanced to take advantage of ribbon FETs and backside metal. The flows and methodologies were optimized for better pin access, better routing quality, and better pre to post routing correlation. That's really key to have much narrower correlation. If you put this all together, Cadence helped improve ISO power and performance by 6% on Intel Foundry benchmark designs. So as you heard earlier, like generational process node gains are now typically 15%. So 6% becomes an enormous improvement equal to nearly half a generation of intrinsic process gains. Now, what's also exciting, I think, is we're working closely with Intel on the potentials of 18AP with the evaluation and optimization such as the adoption of a ULVTLL device. This will help quite a bit. 18AP also has, I would say, narrower design window versus 18A. So both the slow and the fast corners are tighter, even tighter by 3 to 4%. This is really important as you come out with kind of successive, I call it half nodes on a given node, and to see the variation come in is really important. We see this now really for all VT types, boosting design convergence. This is vital, as I said. Then 18AP also has, we see higher, better device, 9% at typical, better current drive. 14% at the slow corners for all device types. So all the goodness of 18A, such as ribbon FETs and backside metal, carries over to 18AP, as Kevin was talking about. That platform carries over, you build on it. These elements can come together to deliver another 8% performance boost, and now you know kind of where that is coming from, and that can be leveraged in several ways. So, there's no rest for the weary, and a successful 18A, 18AP node means that it's important to develop and build efficient migration flows. This is key as you're going to design on the 18A platform, knowing that you can efficiently migrate to 14. So Cadence is working on doing just that with a schematic, circuit, and layout optimized TFM to reap the technology benefits of area, performance, power, and ultimately cost on future Intel Foundry nodes to lower the barrier for designs as they move from one node to the next at Intel Foundry. Now, as I mentioned in the beginning, packaging has become as important, if not more important in many cases in my estimation, than Moore's Law itself. As architectural needs surpass the pace of Moore's Law, it's packaging that comes to the forefront for advanced designs. Intel Foundry has an impressive track record in packaging. And Cadence has been diligent about building a seamless advanced packaging flow to build heterogeneous designs. Some highlights, we have an EMIB reference flow that has been in production with high capacity and performance with solid collaboration across Intel and Cadence teams. Routing automation this year alone is going to provide a 10x productivity improvement. And InDesign analysis tools provide shift left for catching errors early and really greatly improving quality of route. This goes back to the pre and post silicon correlation. So Cadence IP for UCIe advanced packaging and HBM is compatible with industry standard 2.5D packaging technology. Now, it's really how exciting to see the maturity and first major delivery of 18A, a fully EDA-enabled node, and a comprehensive IP portfolio. And it only gets better, as we said, with 18AP as the PPA improves with another substantial leap. And then having achieved the launch of 2 major revolutions in process development, that really sets the base for future nodes. A lot of that investment in that platform with backside metal and power via and ribbon FET really creates this base for future nodes with 14A and 14AE. It's no surprise to me to hear that progress is going well on those future nodes. And then, at Cadence, we're excited, really, truly excited to partner with Intel Foundry and help build the AI-driven future together with Intel's, brilliant technologists and Cadence's, focus on agentic AI-enabled portfolio of tools for productivity, emulation and prototyping tools that I feel really are the envy of the industry, and of course, a world-class portfolio of IP for Intel Foundry, accompanied with controllers, processor IP, DSPs, and embedded IP with the associated, not just IP, but the associated software and systems enablement to build the accelerated compute infrastructure of today that really will solve the physical AI challenges that I've talked about of tomorrow, and that lead us in solving really the hard scientific problems that we jointly will work together on. So together with Intel Foundry, we anticipate a future characterized by increasing mutual customers and truly a flourishing ecosystem. So thank you, and again, congratulations to Intel Foundry on 18A and 18AP. Thank you.